Good morning and welcome to the first ITC Colloquium of 2019. We're very fortunate to have as our speaker today Eugene Chiang. He's a professor in the astronomy department at the University of California at Berkeley. Eugene did his undergraduate studies at MIT, where he got a bachelor's degree in physics with a minor in theater arts. After that, he got a PhD at Caltech, then moved on to be a Hubble Fellow and a long-term member of the Institute for Advanced Study before joining the faculty at Berkeley. He's an expert on all things related to planet formation, so today he will talk about planet formation post-Kepler.
Thanks very much, Antonia. Thank you for inviting me here. It's a pleasure to visit, as always. I wanted to share with you how our understanding, or at least my understanding, of how planets form has been changed by the Kepler spacecraft, which over the course of its 5-year mission to explore strange new worlds, go where no photometer had gone before, has discovered, of course, thousands of extrasolar planets, and in so doing has revised our narrative of planet formation, in many cases by returning us back to certain first principles that prior to Kepler, I think we could only speculate, we could only say, well, maybe these were relevant for planet formation. But now, thanks to the rich statistics of Kepler and just really fundamental measurements of radius, mass, composition, we can now say with greater confidence that these physical processes really were at work to create the planetary systems that we observe today. So this is work that was done over the last 5 years or so with a number of postdocs and graduate and undergraduate students at Berkeley, many of whom have gone on to greener pastures. Here's a bird's eye view of everything under the extrasolar sun. So plotting not just planets discovered by Kepler, but also from all other techniques. On the high mass end, we have Jupiters, the gas giants of various flavors. And on the low mass end, so far, we have the super-Earths. So some people distinguish between super-Earths and sub-Neptunes for convenience. I'll just call them all super-Earths. Anything between a mass of 2 and about 20 Earth masses. Now, try not to be misled by the density of points on this plot, because all of this data was taken from web sources full of biases. Try to pay more attention to the numbers coming from real careful measurements, these numbers reflecting occurrence rates of these various kinds of planets. And it is one of the great gifts of Kepler that I can now go out, anyone can go out to the night sky, point to some random G star and say with confidence that that star is more likely than not to host a super-Earth inside a distance of 1 AU. Okay? It's an amazing thing that we can do this now. And as a theorist, I prefer to understand the rule first. If I feel like I can understand the rule, I might be able to understand the exceptions to the rule, right? And what Kepler has told us is that super-Earths are the rule. Gas giants are more of the exception. And I'll talk about both kinds of planets, but I want to start with the norm.
So Eugene,
yeah.
There is a vacant region, but presumably it's shaped by selection.
Of course, yeah.
So where is the boundary of the sensitivity?
Well, you can see it around here, right? For the transits for Kepler, about a year. You can start. There are a handful of detections for microlensing, which I think is very exciting, and but all of this space will be covered by just for example, a mission like the WFIRST microlensing mission in the future. Right? This is what we look forward to. There's also this region over here, which I think direct imaging is really going to fill in. So here's a plot which one of your alumni and now my colleague made in collaboration with people here. Courtney is pointing out, on this radius mass diagram, the radii coming from Kepler, the masses coming from follow-up radial velocity. what she's pointing out is that many of these super-Earths lie along this radius-mass relation that fits the Earth. So what are these objects? These super-Earths are the closest in super-Earths have the same bulk-like composition as the Earth. So what are they? They're like the Earth, only super, right? So they have the same proportion of silicas to iron as does Earth and Venus. But you'll also notice on the plot that quite a few of these super-Earths, and if you plot all of them as Li Zheng is doing here, the majority of them lie above that boundary, right? So they have larger radii than you would expect from a purely rocky object. And the going interpretation is that these are also rocky cores, like the Earth, except they're overlaid with this thick atmosphere, made predominantly of hydrogen and helium. I've given in to my theoretical prejudice, and I just couldn't help it, meaning no disrespect to Courtney or anyone who makes this kind of plot, but I just had to scratch out these labels, which are labeled by water. Yes, formally, they're consistent with bodies made predominantly of water, but I think we can rule that out now. The water world interpretation basically ruled out, in my view, by HST transmission spectroscopy, right, which shows that they don't have these steam atmospheres. I mean, water world. Rotten Tomatoes, 43%. 3 hours. You choose. Okay, so what are these atmospheres really like? Well, we call them hydrogen-helium atmospheres, but we recognize that they must be highly enriched in metals, maybe up to 50 times solar metallicity. This is in order to have any chance at all of reproducing the high altitude, high condensation temperature clouds, these metal clouds, or hydrocarbon hazes that we infer from the flat transmission spectra. Okay, so highly enriched in metals, but still predominantly hydrogen. Here are the gas to core ratios, so the inferred masses in the atmosphere relative to the mass of the underlying core. This is a quantity that I'll be plotting throughout this talk. So GCR, these are inferred from interior models that fit the observed radii and masses. And you can see that the GCRs, the gas to core ratios, the gas mass fractions are on the order of 1%, right? Give or take in order of magnitude. So these atmospheres, they're huge by volume, but modest by mass. A mere percent by weight of the atmosphere for the entire mass of the planet can double the radius of the object. Okay? This one number of about 1% already, I think, points you to a pretty specific formation scenario for super-Earths. A formation scenario that puts super-Earths, forms them late in the evolution of the protoplanetary disk. Late when there just isn't as much gas left over. Late as opposed to early when the disk has its full complement of fresh primordial hydrogen, right? It's at early times that people construct so-called minimum mass nebulae. By definition, minimum mass nebulae are solar composition disks, so having gas to solids in the proportion of 100 to 1, not 1 in 100. I mean, what would you choose for the formation conditions for super-Earths, knowing that their gas to solid contents are 1 part in 100? Would you choose early or would you choose late? I know what I would choose, naively, and for the rest of the talk, I'm going to give you more physics-based reasons for why that makes sense. A late time formation when the surface density in gas is much less than the original minimum mass value. One reason why a late time assembly in a gas poor, but not gas empty environment is that if you want to form the core in the first place by major mergers, a gas poor environment is the way to do it. So if this looks like a merger tree, that's because it is. This is core formation by giant impacts, otherwise known as major mergers. Okay? Small bodies banging together to form larger ones. This doesn't happen if there's too much gas. Too much gas exerts too much dynamical friction on the protocores, circularizing their orbits, keeping them on nice, circular, nested, orderly, beautiful orbits that are totally boring with respect to planet formation because they don't cross and they don't merge. Richard, did you have a question?
Does the gas scenario have more time to eventually get you a solid object, and what are the differences in timescales? If the gas rich happens earlier, then presumably we would have more time. So the previous
Yeah, that's right. So gas-rich environments are also disfavored for super-Earths for the formation because you also have more time to accrete more gas and explode to something like a gas giant. So that's just another reason.
Against the formation.
That's right, that's right, that's right. Here I'm talking about dynamical friction keeping the protocores from merging. But if you lower the gas density, and we observe these disks to dissipate over millions of years, the gas in the disk can accrete onto the central star. It can be blown away in a disk wind, possibly magnetized, okay? And if you allow that to happen, leaving behind the solids, those solids can mutually stir one another onto eccentric orbits that cross and merge. How much do you need to reduce the surface density by? Well, that depends. That depends quite sensitively on the spacings between protocores, right? There's a merger time scale for an ensemble of